Alright, ladies and gentlemen, here is the practice exam video that goes over the practice questions for your quiz tomorrow, your second quiz on gas laws. This quiz is going to focus mostly on the theory stuff, a little less calculation based, about vapor pressure, a little bit about the gas laws, kinetic molecular theory, ideal gases, and also, well, I did say vapor pressure, right? A little bit also of a throwback to the heat and energy stuff that we covered in the last unit, just to review ourselves. Okay, let's start with number 1 here. According to the kinetic molecular theory, this is the first thing we talked about, all gas particles, what? Okay, do gas particles have strong molecular forces? No, they don't attract each other. They have separated by very small distances? No, they're actually very spaced apart. Are in a random constant straight line motion? That is correct. But let's look at 4. Have collisions that decrease the total energy of the system? No. So here, talk about choice 3. It's random constant straight line. Gas particles are very random. They like to bump into each other, but it doesn't lead to the decrease in total energy. If you think back to the theory for choice 4, instead energy is transferred in collisions. Okay, that's enough of my rant there. Number 2, under which conditions of temperature and pressure does a real gas behave most like an ideal gas? So ideal. That means we want high temperature and low pressure. Low pressure, high temperature. Choice 2, on the other hand, is more of real gases. Ideal is right here. Okay, number 3, a sample of chlorine gas is at 300 K, 1 atmosphere. At which temperature and pressure would the sample behave more like an ideal gas? So that means, once again, we want to see our temperature go up and our pressure go down. So it's got to be higher than 300 and lower than 1 atmosphere. The only one that fits that is 600 K and 0.5 atm. Number 4. Which rigid cylinder contains the same number of gas molecules containing H2 at STP? So same number. For number 4, that means we're looking for same temperature, same pressure, and the same volume. If our container is 2.0 liters, that means we need to look for the same volume, 2.0 liters as well. Okay, number 5. Which 2 samples of gas at STP contain the same number of total number of molecules? Same thing, same volume. Choice 1. Number 6. At 25 degrees Celsius, gas in a rigid cylinder with a movable piston has a volume of 145 mLs and a pressure of 125 kilopascals. So gas is compressed to volume. We're looking for new pressure with temperature constant. This is Boyle's law. This is something we did in the previous quiz, but let's review that nevertheless. Okay, so pressure is 125 times 145 equals, on the other side, we have we don't know what the new pressure is, times our new volume of 80. So P2 is now equal to, should get 226.6. The one that's closest to that has to be choice 4. Do not be afraid if you get numbers that are off the choices. Pick the one that's closest. 230 is close to 226. Now number 7. Let me pick a different color this time. How's purple sound, guys? Number 7. Which temperature change would cause a sample of an ideal gas to double in volume while the pressure is held constant? So temperature and volume. That's Charles' law. That means at Charles' law, if volume goes up, so does the temperature. So they go up together. So if we double the volume, that means we have to also double the temperature. So let's look at them. And we always have to work in Kelvin. So we could cross off 2 and 4 because they're in Celsius. Always work in Kelvin. Choice 3. Number 8. Which phase change is endothermic? Absorb energy. So we're getting hotter. Okay, so gas to liquid? Nope. Liquid to solid? Nope. Gas to solid? Nope. Liquid to gas? Yes. Boiling, guys. Number 9. Which equation represents sublimation? That's a phase change if you didn't know. And that is a solid going to a gas. It's one of those weird ones that you could skip the liquid phase. Think of something becoming so sublime. You're going to a higher state from solid to gas. Okay, number 10. Given the diagram representing a heating curve for a substance. Alright, heating curves, guys. During which time interval is the average kinetic energy of the particles of the substance constant? So average kinetic energy, that's the same as temperature. So temperature is constant here. I'll use a different color for potential energy increasing. Also, same area. So that's BC and DE. The only one that fits that is BC. Now, if you're looking for potential energy being constant and average kinetic energy being increasing, then you would look at the other ones, the ones that are inclined. All right, number 11. Which physical changes are endothermic? Like I said again before, absorb energy. So we're getting hotter. Melting and evaporating. Choice 1 is correct. Melting and freezing, they undo each other. Condensation, sublimation, not quite. Condensation, deposition, nope, not that either. All right, number 12. What is the melting point of the substance given that heating curve? So melting point, that's a phase change. What phases are we going from? Solid to liquid. Think of melting ice as your example. So we're looking for on this graph. So we always start from a solid, going into a liquid, going to a gas. So we're going from solid to liquid. So this line right here, this segment over here, is where we're going from solid to liquid. What's the temperature there? If you look here on the graph, it's about 55 degrees Celsius. Number 13, which graph could represent the uniform cooling? So we're looking for cooling of a substance, starting with the gas phase, going to the solid phase. So we need to see a temperature go down. And if we look at that, choice 4 is the only one that fits the temperature going down. It's a cooling curve. Can you believe this spacing of the questions? You have 2 big questions occupying a page. What a waste of space. Alright, number 14. The graph below shows the heating curve of 1 gram of a solid as it is heated at a constant rate, starting at a temperature below its melting point. Okay, based on this graph, what is the heat of vaporization? Okay, so that means, oops, here it is. Okay, heat of vaporization. So vaporization means the boiling point. We're looking for the boiling point, and it's right here, because we started from solid to liquid to gas up here. So going from liquid to gas, that's our boiling point. And let's look here. What is the heat of vaporization? This is a tricky question we've never worked on before. Okay, so how many calories does this take? We're going from 400 to 800 calories. So take the difference between that. 400 calories measured along line DE. Do not get confused with choice 1. That's going from all the way from the beginning to 800. But no, DE lies along 400 and 800. So it's choice 4. Alright, here, what is the boiling point of the substance? Here, it starts below its freezing point. So we start at a solid. Here is melting. Going into a liquid. Still a liquid over here. And then over here, finally changing into the gas point, gas phase. So how did I know that's at these points on the table? If you notice here, constant temperatures indicate phase changes. I'll write that again. Constant T, phase change. So boiling, we're going from liquid to gas. We should know that the temperature of that is 54 degrees Celsius. Okay, number 16 through 22 only take up one column. I wonder where the rest of the questions went. It's a blank space here. Number 16, rigid cylinder contains a sample of gas at STP. What is the pressure of this gas after the sample is heated to 410 K? So, T is 410. Okay, well that's T2. T1 is standard temperature. That's 273 K. P, initial pressure, standard pressure, that is, let's pick 1 atm. We gotta figure out what P2 is. So that's interesting. What happened to volume? We can still use the combined gas law here. Now because we could assume that the volume is constant because we're in a rigid cylinder, we could just cross up those V's and just deal with P over T. Okay. So let's plug things in, plug and chug everybody. I hope it's water you're drinking. So for P2, and you get 1.5 atm. Oh my god, I didn't even check to see if we were working in kilopascals with the answers. Luckily, we picked atm. Choice 2. Alright, number 17. A gas occupies a volume of 444 mLs at 273 K and 79 kilopascals. What is the final Kelvin temperature? Alright, another gas law equation. Alright, if you take a look at this numerical setup, this is what the equation should look like. And I'm going to calculate the answer for you guys in a moment. Now this looks like a proportion. I highly suggest that you guys treat it like a proportion and do cross multiplication. Some of you guys still struggle with the math. I hope using it like a proportion and doing cross multiplication will help you guys. And so you should get a temperature of 566 Kelvin, choice 4. Alright, standard pressure is equal to, well, if you don't remember what it looks like, you could always check the reference table. It's at the front page. And that happens to be 1 atm. Number 19. At 65 degrees Celsius, which compound has a vapor pressure of 58 kilopascals? Alright, for number 19, you have to use table H. So, after you look at that, find 65 degrees Celsius and 58 kPa, and you should get ethanol because it's the closest one to that point. So you find the point on the table, on the graph, and you find the line that pretty much is closest to it, and that's ethanol. Now number 20 is also another table H question. What is the boiling point of ethanoic acid? So you find the ethanoic acid line. Find ethanoic acid. And you need to find where it's 80 kPa. Find 80 kPa. And you should get about 111 degrees Celsius. That's approximately where it crosses the line. Now number 21, at which temperature is the vapor pressure of ethanol equal to 80 kPa? So once again, you find the ethanol line where it crosses 80 kPa, and that should be approximately, let's find ethanol, kPa. That's a little under 75 degrees. Hello there, 73 degrees Celsius. Number 22, which compound has the lowest vapor pressure of 50 degrees Celsius? So find 50 degrees Celsius look for the line that has the lowest vapor pressure, and that should be ethanoic acid. Alright, we're almost through, guys. Now we're finally on to the short response questions. Let's change some colors in here too. I'm feeling green and a blue and a purple still. Okay, let's go back to green. 23. Compare the average distances between the helium atoms in trial 1 to the average distance between the helium atoms in trial 3. Okay. I highly suggest you look at these two things. The volume. Volume, what is it? It's space. So more volume, more space, which equals more distance. So trial 3 has greater distance because there's more volume. Alright, number 24. Determine the pressure of the helium gas in trial 4. Okay. So if you follow the trend of this right here, that means this thing will also be 0.412. So you can just do the math. 0.412 equals 1.373 of P4, and you should get P4 is equal to whatever the value is if you do the math. Should be approximately 0.3 atm, just about. State evidence found in the data table that allows the product of pressure and volume for the fourth trial to be predicted. So, once again, doesn't seem to change. Alright, number 26. So we have this prompt here. Ethane, C2H6, has a boiling point of negative 89 degrees Celsius at standard pressure. Ethanol has a much higher boiling point than ethane at standard pressure. At STP, ethane is a gas and ethanol is a liquid. Okay. That's an interesting thing. Liquid boils when the vapor pressure of the liquid equals the atmospheric pressure on the surface of the liquid. Based on table H, that means you need table H next to you, guys. What is the boiling point of ethanol at standard pressure? So if you look at table H, there's that dashed line. That's where standard pressure is, if you didn't know. What is the boiling point of ethanol? So let's find where it crosses that dashed line. And it is about 74, no, a little more than that. What am I thinking? That's over 75. It's about 80 degrees Celsius. Alright, 27. Here we have this prompt for our last set of questions. Cylinder A has a movable piston, contains hydrogen gas. Cylinder B has methane gas. And here we have same pressure, same volume, same temperature. I wonder what that means. Okay. Show a numerical setup for calculating the volume of the gas in cylinder B at STP. What? Okay. So, this wants us to use the combined gas law. Knowing that we're changing to STP. So I'll show you the setup in a moment. Okay, so this is what they want in terms of numerical setup. That's all you need to show. Now, on the quiz that I showed you guys had to calculate the answer. That will never be enough for me to just have a numerical setup, guys. And do not forget units. Naked numbers mean nothing to me. So that's why you gotta dress them up in units. That's how we give meaning to things. Alright. Should get a volume of 1.4 liters approximately. So that's if they ask for the answer. They don't want it, but I want it. Okay, 28. State a change in temperature and a change in pressure that will cause the gas in cylinder A to behave more like an ideal gas. So ideal, again, you want to raise what? The temperature and lower the pressure. So you can give any number that's higher than the temperature and lower than the pressure. All right, now let's go on to the last question. Compare the total number of gas molecules in A to B. So notice here, same pressure, same volume, same temperature. So that means same number of molecules. Remember Avogadro's law, guys. Yay, we finally finished. Do not worry, guys. There are only 15 questions, 13 multiple choice. 2 of them are short response where you kind of write stuff like this. No actual calculations like I made you guys do in the first quiz. I hope this was helpful for you guys. I was a little bit more animated with this video than I was in the physics videos, admittedly. Just because actually chemistry is a little more interesting to explain, in my opinion. Don't tell